Okay, so here I have a graph of a sound wave, and in this video I'm only going to show you the graphical representation of a sound wave, and not the visual representation with all the grains, right grains and all, because it is just difficult to set up. So here on this axis I am plotting the distance in meters, and here I am plotting the pressure, which indicates the crowdedness of air particles in a given region. So if I see here I have a crest or a compression in visual terms, and the pressure at that crest is around 2 units. See, this is the crest, and if you go here, you can see 2 units of pressure at the crest. Now, if we move further ahead, the pressure drops, and here it reaches a minimum of around zero, close to zero, and then it rises again, and it at this point it again reaches 2 units of pressure. So if we see from one crest, we have to go to another crest for the same value to be reached again, right? So here we had the value 2, it we so the value dropped, then increased again, and at this point the value became again 2 units of pressure. So if we see that the pattern after this, the pattern again starts repeating itself, right? So again the pressure drops and starts increasing again. So the unique pattern is from this point to only this point. After this, the pattern again repeats itself. And if you look at the complete wave also, so you can look at the complete wave. See, the pattern is just repeating itself. So the pattern is only unique between. So the pattern is only unique from this point to this point, or from one crest to another crest. After that, it repeats. So what is the distance between, so how long is that unique pattern? So here I have, it's 1.5 distance, the distance is 1.5, right? So that is 2, that is 0, so that should be around 1.5 meters from the point I am measuring the distance, and I have a crest at 1.5 meters. If I move ahead, I reach here, and this is 8, around 8. So the next crest is at 8 meters. So 8 minus 1.5 gives me 6.5. So the distance between the first crest, this one, and the next crest is 6.5 meters. And that is the length of the unique section of the whole wave, right? After that, it just repeats. So this is what we call one wave. Okay, the distance between this part of from one crest to another crest is one wave. And we can also visualize this in terms of the oscillating object. So if you remember, at this point the oscillating object uh, has pushed the first crest, then it moves back, the oscillating object moves backwards, and it forms a trough, then comes back again forward and forms a second crest. So while we go from here to here, the vibrating object has completed one whole oscillation. It has moved from the rightmost point to the leftmost point. So here it was at the rightmost point, it moves to the leftmost point, and then comes back to its rightmost point. So the in this duration, the object also has completed, the vibrating object has also completed its complete oscillation, and that is, so, and it gives me that one unique part of the section of the wave. After that, even the object repeats its oscillatory motion, and the wave also keeps on repeating itself. So this is what I call one wave. So this section is one wave, and the length of that one section, or the length of that one wave, is called, obviously, one wavelength. So what is the wavelength of this particular wave? Well, I just found that the distance between two crests, or the unique part that I was talking about, is 6.5 meters. So the wavelength of this particular meter is 6.5 meters. So obviously wavelength has to be in meters, it's a length. And now I can just take another wave with a different um, frequency, and yeah, see, let's say of a different wavelength, actually not frequency. So yeah, now I get another wave with a different wavelength. So just give it a try to find out the wavelength of this wave. So yeah, now that you've given it a try, Obviously I know you did not, but if you did, um, so you can find the distance between the first this crest, let's say, and that crest. So that crest is at around, so this is 2, that should be 3, so this should be 2.5. So it's close to 2.5, and this one is close to 4, 5, close to 4.75. So I can subtract those two numbers, 4.75 minus 2.5, and I get 2.25. So 2.25 meters is the wavelength of this. But if you observe, the distance between these 2 points is the same as the distance between these 2 points. So if you find the distance between these 2 points, that should also that also seems to be equal to these 2 points, right? And in fact, so you can actually use either of the two definitions. So you could either find the distance between two crests, and that would be a wavelength, or you could find the distance between two troughs, and that would be a wavelength. And in fact, I have a third way. So what I can do is I can just, yeah, I can just take the wave as this. Now what I see here is, so if I observe these points here, what do these points indicate? So this is the maximum pressure that I have, this is the minimum pressure that I have. What is this value of pressure? Well, this value of pressure is the normal atmospheric pressure. I hope you can understand that, right? This is halfway between the highest and the lowest pressure. So this should be the medium wala pressure. So this is the medium wala pressure, or the pressure that is normally there when there's no sound. So at these points there is no compression, no rarefaction. So here you have a compression, here you have rarefaction, but here you have nothing. It's just normal air. No, not being compressed, not being spread out. It's just simple air. Such a point on a graph of a sound wave, or even in general, is called a node. um, so you'll learn more about nodes later, but yeah, here all you need to know about nodes is that at the node you have medium kind of pressure. So here you have the maximum pressure, here you have the lowest pressure, here you have medium level pressure, and that is the pressure that is normally present around us. So that is the air pressure. So now how could you use these to find the wavelength of wave? Well, you could simply count three nodes, 1, 2, 3, and you can actually so that if you find the distance of covered by three nodes, so the distance from here to here, so that's three nodes, right? 1, 2, 3. So this distance is also a wavelength. And yeah, one final note, I would just like to confirm this part by using a scale. Okay, so I don't have a ruler right now, but what I have is a compass. So I can also use this to find the distance, actually compare distances. So yeah, if I see here the distance, this is the distance between two successive, or one after the other. So two successive crests. So that is the first crest there, this one, and this one is the first crest, this one, and that's the second crest, and this is the distance between those two crests. And if I measure distance between two troughs, well, that is the distance between two troughs. And yeah, you can clearly see that the distance between two troughs is equal to the distance between two um, crests, and that is equal to the distance between, so this distance covered by three nodes. See, so all those three distances are the same, and that is equal to the wavelength of a wave. That is it for this video. Bye.